Okay, let's make sure that's on. Okay, cool. All right, well, thank you for having me. So this talk is going to be a mix of, a kind of a recruitment talk for Los Alamos. I think lately Los Alamos has been in the news a lot, especially with Oppenheimer. So I assume most of you are familiar with where Los Alamos is and what they do, but I also want to talk about the technical work we're doing because it's actually very diverse and, of something I'm very excited about. Uh-oh. The mouse. There we go. Okay. You don't have to read this. This is for me because I write these slides and then I don't look at them for months and I forget. But basically, for decades, Los Alamos has been at the forefront of deterministic transport research. We have these codes that have existed for decades, and we've developed a lot of the methods that you see sometimes in your textbooks, right? The people who write textbooks for transport at one time or the other were actually Los Alamos scientists. So we're sort of proud to be, at the forefront of all this research. And as HPC, high performance computing, and scientific computing become more and more important, like the best way to see a lot of these advances is in the transport equation because it's just so complicated. So I'm going to talk about the work that different teams at Los Alamos are doing, what some of my technical work I'm currently doing, and any actual opportunities for you to maybe come out to Los Alamos for a summer or for a year or for work if you're interested. So outline, we'll skip about me. I'll talk a little bit about Los Alamos just to give you a refresher. I'll talk about the group that I am. Los Alamos is divided into groups, each with its own technical focus. I'm in the computational physics and methods group. We'll talk about some radiation transport, and that is not only just neutrons, but also X-ray transport and charged particle transport, because we're all very interested in the different applications of these physics. Then I'll get into some block AMR work, which is automated mesh refinement to make solving the transport equation cheaper and more efficient. I'll talk about something called tensor train neutron transport, where tensor trains are really big right now in machine learning and how those can be leveraged to solve the transport equation. I'll talk about machine learning for group structures that we've had students be the main pushers of, and then finally a recruitment pitch: come work for us. This is just my bio. Don't worry about it. Los Alamos National Lab originally founded during World War II as part of the Manhattan Project, and currently we're about 14,000 employees. About 1/5 of those are PhDs. So we have 460 postdocs. So it's something to keep in mind, especially as you're finishing up your PhD. Los Alamos hires a lot of postdocs, and they're very competitive. During the summer, we host about 1,800 students. This goes anywhere from high school students to undergraduates to grad students on the verge of finishing up their PhD. So currently, it's run by Triad National Security, which is this you don't really have to worry about the details, conglomeration of private companies and universities. And we're primarily funded by the Department of Energy's NNSA, which is the National Nuclear Security Administration. So we have a big emphasis on national security, research. This is all LANL. LANL has very specific focuses it wants to, it looks towards the future, and this is what it wants to focus on. So some of the main things are information science and technology. I think we're all well aware of how important, machine learning and AI is becoming or already is. So Los Alamos wants to be at the forefront of the technical research and information science and technology. Materials for the future, if you're a fusion person, that there's so many materials out there that would be great to somehow get or somehow be able to make cheaply. Los Alamos wants to leverage, high performance computing and advanced scientific computing to see if we can discover how to manufacture these materials to, make something like a fusion reactor possible. Nuclear and particle futures. I think this one's, basically there has to be, you can't forget about the basics of the physics that we're talking about. Neutrons and nuclei and atoms exist, and we have to keep continuing research into that because everything that we do fundamentally comes from these things, right? So people should still be interested and not lose the trees for the forest. And finally, the science of signatures. And this is this is kind of interesting to explain, but it's integrating nuclear experiments, theory, and simulation to understand complex nuclear phenomena, right? Do we really understand everything that happens in the nuclear reactor, right? Can computation help us, gain some insight? What are the limitations of computation? how confident are you that your simulation is representing reality? And it's just sort of, putting, error bars in that. So I'm in the computational physics and methods group CCS2. The letters don't mean anything. And our motto is performing innovative solutions of physics phenomena on tomorrow's scientific computing platforms. So the CCS division was formed to primarily strengthen the visibility and impact of computer science and computational physics research on the strategic directions for the laboratory. You all, I don't have to sell it to you, but you all know how important simulation is, right? Designing an experiment, an interesting experiment, can be billions of dollars, right, over years, and any sort of failure is incredibly bad, right? We have to be worried about how these things get funded, right? So simulation, gives us some insight before we design experiments, before we go run off and try crazy things. And so we should invest in simulation as much as we do in experimentation. And so that's the kind of the second point, right? Both computer science and computational science are central to scientific discovery and innovation, right? You can't have experiments without simulation, right? Somebody very important with a lot of money will ask you, well, how do you know your experiment will actually get you the data you want? And simulation is sometimes a really good way to answer that question. And so CCS division forms a bridge between external partners, for example, universities and other industry, and the lab programs, trying to bring in like new ideas and technologies to bear on important problems of interest to the lab, to the nation, and to the world. And the idea is that we attract very high quality staff people who are really interested in these problems to generate this sort of like, critical mass, pun intended, of, really good scientific computing people to make me push the science even further. And so now to get a little smaller, right? So, Los Alamos has a transport project, and this basically means that there's a couple of teams that do, transport research and, are responsible for codes that go ahead and solve this equation. And they have various different users throughout the lab and throughout the country. So really what we're delivering a product, and that's a radiation transport capability software library. And as somebody who remembers being a grad student and just worrying about research, it's actually a really interesting transition to go into, like, now you are responsible for a product software, right? Like, it is to some extent, like, you have customers, they have needs and wants, you have a budget. How do you work around that while still trying to do really interesting, research that you can publish? So Los Alamos has created these teams. Capsaicin, which is a X-ray thermal transport code using finite element methods and unstructured meshes. That might mean something to you, it might not. The idea here is just the diversity in different methods and applications that we have in the group. And we all, cross collaborate. So that actually is like probably one of the benefits of, putting these teams under one group. We have JN, which is X-ray thermal transport using Monte Carlo. So, we have, Los Alamos has a Monte Carlo group that does MCMP, but we have another code that does, Monte Carlo for X-rays. And so once again, we're not picky about the methods that we're doing. We're just trying everything and see how good we can get these to perform. We have PARTISN, the team I'm a part of, which is neutron and gamma transport using deterministic methods on structured meshes. This is the SN method, right? And, if you are in the lecture tomorrow, I'll talk about, the advantages and disadvantages of that and why, we focus so much on SN structured meshes. And then we have MACATAC, which is neutron transport Monte Carlo using continuous energy Monte Carlo, right? So we run the gamut from Monte Carlo, deterministic, multi-group, continuous energy, structured meshes, unstructured meshes, right? And you're like, why not focus on one? Well, it's because you're not sure which one is the best for all the problems that you're going to look at, right? So you should give users a wide array of options. Each library is massively parallel and runs on the latest high-end performance computing hardware. We're always worried about what's the next up-and-coming HPC system. What does Intel, what does Cray have? Because we have to be performant. So that's an engineering problem, right? How do you write code that works well across different, companies' ideas of what they consider a GPU is something that drives you crazy sometimes. But you have to be able to, adapt to that. It has to be massively parallel, as you all know, right? Like if you want to do a full reactor benchmark simulation problem, right? These problems get big really fast, right? Parallelism gives you a way to solve, make this more tractable. So as you scale up in the number of resources that you have, the performance of the code should scale with it, right? And that's actually a very hard problem to solve sometimes. We have 20 staff. We have students, graduate, undergraduate students who are there full time, and we have a lot of postdocs. We're all very multidisciplinary. I'm a nuclear engineer by training, but I work with other kinds of engineers, physicists, or applied mathematicians, as well as HPC people and CS people. So like I said, it's the diversity of the group that really allows us to like, stretch out into all these different methods and be effective. So, all our codes are just approximating variants of the Boltzmann transport equation. So here we have the linear transport equation for neutrons, and I actually messed this up because I put a k eigenvalue problem, but there's a source on the right-hand side. Sorry. But we're all solving equations similar to this, right? And nonlinear thermal radiative, transport equation for thermal X-rays has this form, right, which has a very nasty nonlinear term, right? But at the end of the day, all these physics are somewhat similar. All the mathematics are somewhat similar, right? So leveraging, different experiences solving different kinds of physics actually might give you insight to solving another kind of physics. And I'm sure you all know that solving this equation is incredibly expensive and painful. It's a 7-dimensional solution space, velocity, and time. And if you're right down the linear system of equations, this turns out to be, billions, sometimes trillions of unknowns, right? You can't do backslash in MATLAB to solve this sort of problem for anything outside of a 1D slab. So we have to be clever. I've talked about, we have different users. So who are these users, right? Who cares about whether or not we're actually solving these equations effectively and correctly, right? So we have people who do at the lab who use our codes to do, for example, reactor simulations, right? Safety is very important. We obviously have that criticality safety, right? Being able to do K effective eigenvalue problems, isotope depletion, right? Looking at the long-term, evolution of nuclear fuel in reactors. Shielding, obviously, very important, right? If you're designing experiments at the lab that, has fissile material, you better hope that your shielding is good enough to not hurt the people who are working with it day in and day out, right? Are you going to trust simulation to give you those answers? You will, but you need to be confident that the equations are being solved correctly and that the software doesn't have bugs. And software always has bugs. But we also have, some interesting applications in medical, like brachytherapy and cancer. People will use these codes to simulate, cancer treatments. Oil well logging is a really interesting one where companies will come in and be like, we want to know if there's oil at the bottom of, some trench in the ocean. Let's use this software to give us an idea whether it's actually there before we actually spend billions or millions of dollars trying to look for it. But we also have people looking at things like supernova explosions, right? Things that we cannot like model here in the world, right? And they're really hard to look, find all the time. So let's see if we can get into insights into supernovas by using simulation. And then nonlinear transport of X-rays, NIF is like a really big one, inertial confinement fusion research. Like these people use these codes to like, gain insight before they design an experiment or as they're designing an experiment. So I'm going to go through some of the code teams, right? So, just so, I give everybody, I am on the PARTISN team. I really love PARTISN, but, other people are doing really interesting work. So capsaicin is X-ray thermal transport. It's a collection, it's a finite element transport library for general mesh topologies. That means that you can model really complex, physical objects using this finite element method. And it's in C++. One thing that we do is we write codes in a lot of different languages. And this code is in C++ specifically. And this one has, 3 temperature. That means that the ions, electrons, and radiation can have their own temperature, time-dependent radiative transport. We have steady state radiative transport. We have non-local tensor diffusion. If you've seen, the diffusion equation, that's something like that. And they have a heavy use inclusion of, third-party libraries like Trilinos or Parmenas, right? They are the code that goes out there and looks at what is being done in the world of computational science and tries to leverage that to solve their problem, right? So they are, like, let's use the best of the best that's out there and incorporate it into our library. JEN is the X-ray Monte Carlo code. This is object-oriented C++, which actually has a lot of similar code with capsaicin. When you're writing code, right, that is supposed to last for decades, you reuse a lot of code to make sure that stays up to date. And so, leveraging that like saves you so much time. It's also multi-physics. That means it could interface with like hydro application code. So if you're doing ICF where you care about the fluid motion of materials, right, it's able to be coupled. It's massively parallel. Monte Carlo methods are embarrassingly parallel. So, how do you can write a code that leverages that to solve incredibly complex problems quickly and efficiently. And this is sort of the code that gets used on different, chips that get released, for example, by IBM or NVIDIA to test out what are these companies doing, what's their computing performance, can we, take advantage of these sorts of things. So this is the code that we use to do that. And PARTISN is, my code team. We focus on providing computational solutions to the linear Boltzmann equation for neutral particles, gammas, and neutrons using the SN method. And we have a lot of really interesting things in there. For example, moving material corrections, energy group treatments. How do you treat the group structure of the cross sections? But we also do things like, structured meshes and block adaptive mesh refinement, right? And I'll get into that in a second. So since I'm a PARTISN team member, now we're going to go deep into PARTISN. So PARTISN stands for Parallel Time-Dependent SNs, really stretching the acronym there. But we solve both the static and time-dependent forms of the linear Boltzmann equation. We solve this in the forward and the adjoint modes. One of the big emphases that I personally didn't see in graduate school a lot is actually this time-dependent thing. All the interesting physics in the world, in reality, are time-dependent. And sometimes I feel like, you take a class in numerical methods and they talk about Euler, or Crank-Nicolson, and they just sort of wave it off as like, you don't have to really worry about that. That's more advanced. Turns out everything that you care about has time dependent, right? So we have a lot of really cool time schemes in there. We do static eigenvalues, K effectives, and alpha eigenvalues. We do time-dependent stochastic neutron transport equations. So this is things like probability of initiation. I'm not sure if you're familiar with probability of initiation is the probability that if a random neutron comes into your supercritical system, it will initiate a neutron chain reaction that diverges in time. Because theoretically, you can have a perfectly critical system with no neutrons in it until something comes in and kickstarts that process, right? That's a probabilistic problem. We also have moments of neutron and fission numbers, right? So without assuming too much background, the neutron transport equation or the transport equation is only valid for like ensemble averages. You have a lot of neutrons in your system. But what happens when you only have a couple of neutrons in the system, right? At what point do you go from stochastic to deterministic? And so, where is that transition point? And you can actually write down equations to give you insight into that. We can solve those equations. For the lecture tomorrow, I'll talk a lot about discretization strategies, right? We're written in such a way that you're able to plug and play different quadratures, different multi-group and energy treatments, different schemes in space, different schemes in time, how to deal with negative fluxes, right? We all know there's no such thing as a negative flux, but your numerical methods don't know that. How do you deal with those? So we have this sort of plug and play ability to try to figure out what users can do to solve their problem. We also have acceleration via diffusion synthetic acceleration, DSA, if you're familiar. It's just preconditioning. And there's so much theory on that you could read the entire chapters in Lewis and Miller about it. And then we have, parallelization. Like I said, I talked about like we really care about performance. How do you parallelize this, this problem? Like we do this decomposition, 2D decomposition in space, where you actually split cells or blocks across different MPI ranks, and each MPI rank solves its part of the problem and communicates information. How do you balance, the amount of time it takes to communicate a bunch of angular flux information with the gains you get by decomposing this problem? We do all that. And so my day-to-day job when I'm not traveling and talking to students is, we add new physics, we develop solution methods, but we're also trying to write better software to help users understand their problems. At the end of the day, I sort of have a customer service job where some scientist at the lab or elsewhere comes to me and is like, I have this neutron transport problem. What's the best way to solve it? What do my results mean? How do I trust them, right? And trust is a very important thing. So our users perform a wide variety of 1D, 2D, and 3D calculations. So we always require robust and efficient methods for reducing the iterations, right? If you can think roughly, each iteration is the cost of a calculation, you're always looking to reduce that, right? If somebody's running a bunch of 1D problems, they might be perfectly fine, but the instant they add any sort of three-dimensional like behavior, you're super slow. That's not going to work. So we're always figuring that out. So we've always been, long involved with work in like criticality safety, reactor engineering and shielding, sensitivity analysis, and inverse problems. And like I said, now we're also beginning to apply these methods and solvers to really like non-traditional areas, such as the R process in supernova collapse, right? Yeah, you can, neutrons show up in a lot of places, leverage, users, leverage codes that have, a pedigree that have been there for a long time to maybe solve those problems and give you some insight. So the PARTISN code generally, we have 6 dedicated team members and plus or minus some students depending on the time of the year. I'll go through some of them. You might have seen these, I'm putting out these names out there. So if you ever meet them, go talk to them. They're really nice. I work with them all the time. Erin Davis is the group leader. Her focus was on stochastic neutronics. Nathan Hart is our GPU person. He's really good at, writing these algorithms to be solved on GPUs because GPUs are so different from your traditional CPUs. That's me, Mario. I do a lot of block AMR, discretization in space. So I've learned a lot of that. Tommy Saller is our team lead. He has tons of knowledge on cross sections. As you're all are well aware, cross sections are incredibly complicated, and we don't know how good they are. So you need to sort of figure out, like, build an intuition. Joe Zor is another GPU HPC person who's great at every single sort of novel architecture that comes out. How do you port code that works on everything? And then John Dahl is general expertise and years of code knowledge. One thing I like to point out, we actually have PhD students who do a lot of their work in PARTISN. Jawad Musa is doing stochastic neutronics. He spent 2 summers at the lab implementing his grad research in the code itself. It's part of the code. So there's possibilities of you implementing something really cool there if there's an interest. But some of the things that we've developed in the last couple of years are methods development, material motion, and advection algorithms. You can write the transport equation, but what happens when the material behind it is moving really fast, right? Those neutrons are being pulled, so the equation changes. How do you solve that? You can imagine, in like reactors that you have, liquid fuel where like your neutrons actually are being forced up. It changes the physics. You have to write a different transport equation. We can do that. Using machine learning to improve multi-group data. When you discretize the transport equation, you have to do something about energy. In the deterministic case, we do multi-group. So that means you select a group structure and a weighting function. How do you know that the group structure you picked is good? Experience is fine, right? When you're doing the exact same reactor for the last 60 years, which we've sort of been doing. But now that we're looking at like really interesting novel reactors, that intuition carry over? The answer is most likely not. So how do you develop a systematic way of testing that? We have self-shielding corrections for multi-group data. I'm sure you've all heard about self-shielding in reactors. How do you manipulate the cross sections to take into account a very important physics? We have the stochastic neutrons. We have block AMR, which I'll talk about in another slide, and efficient and scalable computational transport solutions for massively parallel architectures using MPI plus X paradigm. What that means is I'm going to use MPI to leverage, an HPC system. Do I use threads like OpenMP? Do I use GPUs? How do I distribute work to make that very efficient? So not very obvious things until you actually start doing it. And it also can be very problem dependent. And there's also the day-to-day of like bug fixes. Sometimes I've spent weeks looking for a bug, right? And part of being a good scientist is realizing that, hey, I got a K effective that doesn't look quite right. You go in there and you're like, wait a minute, it's because there's a bug. For example, the other day I was like, that answer looks, it's supposed to be 1 exactly, and it's like 1.01. You're like, that's pretty bad for a reactor, right? Turns out I had put in a factor of 2 into the fission cross section because I was doing some other debugging. Like that's kind of like, and I'm sure you've done that all before, where you're just like, I put a factor of 2 somewhere, right? And you spend weeks looking for it. But that's what we do because over decades of developing a code, you do things, you make mistakes, right? And there's nothing wrong with that. You just got to make sure you figure out how to find them and fix them. PARTISN is written in Fortran, actually. So we're doing a lot of code modernization. And that doesn't mean that we're doing C++. That's just we're doing more modern Fortran. And for anybody who can't see me, I'm doing, air quotes. Basically, like rewriting an entire code that works really well in a new language is an expense that will require a lot of people's time. Maybe you don't want to do that. Maybe you just use more modern Fortran. So we're spending some time doing that. So that's what my day-to-day looks like. And we also provide user support. There's, listservs, people send us emails. They want to help running these codes, how to build these codes and understanding the results, right? It'd be one thing if I just told you how to run the code, right? But I'm also there, I theoretically have a PhD in nuclear engineering to help you interpret the results and figure out whether or not you gain any insight into them. And actually, if you're interested in the code, it's actually available through RSIC and is currently installed on LANL Livermore machines, right? So you can go through RSIC if you want to install the code. So this slide here, getting a little deeper into the team members is just sort of me to tell you that there's like a very diverse set of perspectives and focuses that a team has. So, even if you don't do, quadrature research, or you're not interested in deterministic SN, a lot of people came in from different backgrounds. And these different backgrounds are actually really good for writing a really good transport code and developing interesting methods, right? So here I list a couple of the PhD topics. People did everything from stochastic neutronics to SP2 approximations that I don't even understand to this point, really, to alpha eigenvalue problems. And the point, this slide I think is here more for me, is to tell you that what you do in your PhD doesn't necessarily mean is what you'll do at the lab. Because I don't know about you, but towards the end of my PhD, I wasn't really all about my dissertation topic. So going somewhere where I was allowed to have a breadth of new research experience was really good and really great. But I learned a lot that I was able to leverage. We also come from a bunch of different schools. We're not just all from one university or from one part of the country. We're always looking for people across the country. Okay, that's a lot of background. Let me actually get into some technical work with the time that I have. So my current work is focusing on what we call this block AMR method, which is a block automated mesh refinement. And so the idea is to split the spatial domain. You can sort of think of this as like a reactor assembly, and have different levels of refinement or coarsening depending on what's important to you, right? For example, if you want more detail where you have fission cross sections, you would put more cells there. And where you don't have it, for example, in water, you'd put fewer cells. What does this do for you? Makes it actually way simpler to solve, right? You use a lot less memory. And sometimes that improves your time to solution. One of the things that we're running into, though, is load balancing. You can imagine, we really like lines of symmetry in our physics problems. So you can imagine, like, if you distribute this work across a bunch of MPI ranks, there might be a couple MPI ranks that have a lot more work than others. Some MPI ranks might just have all their cells in like a water zone. They complete their work immediately and are start waiting, right? And we all know that the slowest MPI rank is the one that determines your solution time. So how do you effectively load balance this? So that means I get to go into the literature, in CS, in other computational physics, and try to develop load balancing techniques that would make these these savings in memory worth it, because we're actually not killing ourselves on load balance. And so I mentioned here we decompose it across MPI ranks. We do it across the x-axis. So for example, here you can have 5 MPI ranks. Rank 1 would have this number of cells. You can think of each color as a different amount of work. The second one has this one, and so that's where you actually end up with the potential load imbalance, right? For example, if these were all red cells here, one rank would have a lot more cells than the last one, right? How do you balance that correctly? A very obvious way is to actually not use this 2D decomposition and actually just distribute the blocks, based on which rank has the least amount of work, like a round robin approach. But when you're solving the transport equation, which is a hyperbolic equation, you actually sweep. And so if you do really good load balancing, but your sweep ends up waiting for a bunch of blocks to finish, you end up way slower. Transport sucks. Yeah, it's very difficult. It has a lot of physics in it, right? So you got to be really careful that you just don't take an off-the-shelf, fluid mechanics approach and try to apply it to your physics, because your physics might not like it. Transport doesn't suck. I love it, but like it can't, it keeps you up at night sometimes. So that's what I spend, part of my time doing. Something I'm really excited about, we actually just published a journal paper is using tensor trains. Without getting too much into specifics, tensor trains are a way to express multi-dimensional data arrays in a compact form using tensor products. So the idea is that if you have like a 60 tensor, it can be somehow decomposed into smaller elements that when you multiply out, you actually reconstruct the full 6-dimensional tensor to some error. Those things can be very powerful because you can actually do linear algebra on them, right? So if you were to go through the process of discretizing the transport equation, you end up with something that looks incredibly nasty with a bunch of indices, right? And so you have the number of groups unknowns in G, the number of groups in X, number of groups in Y, Z, and the number of ordinates. We all know that the discretization for a neutron has to be on the order of a mean free path. In a reactor, that means you can end up with tens, like 100 billion unknowns. You can't construct that matrix in MATLAB. You won't be able to. But what if I could say we could actually construct those linear operators in a tensor form that is compressed? And so that's what we've been working on. And so you can show that you can always write transport operators as these Kronecker products of matrices and vectors, right? So I end up generating a linear system AX equals B, but I actually don't create A. What I'm instead creating are these like smaller, much more tractable matrices and vectors, and then I use a Kronecker product to construct the solution. So doing, this looks kind of complicated, but what you end up with is just an operator form of the transport equation, in this case for a k-effective eigenvalue problem. So as the number of unknowns increases, the sign of the linear system becomes untenable unless you can express these as in some sort of compressed format, which machine learning people and data science people have been doing for the last 10 years. So the tensor approach, right? So instead we think about matrices, matrices are 2D. We think about linear algebra. 2D makes a lot of sense to us because that's what we're taught. Tensors make a little less sense. 3D tensors make okay sense, but I can't imagine 4 and 5-dimensional tensors, but we're okay with 5-dimensional arrays. So instead of flattening the operators into matrices, work on them as tensors. Go into 6 dimensions, into 5 dimensions. You'll have different matrix operators based on your boundary conditions, but you still have these like objects that you can manipulate as you will a matrix. And so the idea here is, for example, if you have this is a very simple example, you have this matrix here that is, I think, 9 by 9. Each single element can actually be constructed by the Kronecker product of these vectors. So here you only need to store 12 elements. This matrix has 81. So you actually end up saving, you're compressing it. So that's sort of the idea. And I use a lot of pictures because it took me a long time to understand. But what this it's basically, if you're familiar with a singular value decomposition for matrices, it's the same idea except for tensors, where you actually take smaller 3D tensors and matrices and construct some sort of like truncation that reconstructs the operator, and where these elements are, so you can always access them. In like MATLAB, you can do A111 and knows what element it is. You have a prescription to figure out every single element, and if you have the prescription for every single element, you can manipulate it. And so for neutron transport, you can show that when you do SN, diamond differencing in space, multi-group, that the decomposition is exact for when there's only one material, which is like a limitation, sure, but this is, more like, this is really interesting work, and hopefully we'll expand it to multiple materials. But when I say the decomposition is exact, I'm saying that by writing the operators in this form right here, I haven't incurred any sort of compression error. I do have the error from the discretization, but I haven't polluted anything else, right? So by being able to write that exact, I can go ahead and create these tensor train representations, and they end up looking like this. And this is all very fancy math, but all this is matrices and vectors in MATLAB. And you do this conversion process. So you end up with operators that only grow linearly in the unknown. So instead of having this like explosion of number of unknowns, you keep this manageable. The explosion of unknowns is called the curse of dimensionality, right? If you have a linear system that has m by m elements, and you were to double the number of elements in X, so now you have 2m by 2m, you've actually gone up to 4, right? You've squared it. So instead, this is a linear growth, and that saves you a lot. And so we, in the journal paper, we went ahead and tried a 3D problem using 256 energy groups, 512 spatial cells in X, Y, and Z, and use an SA quadrature. This is a really, really big problem. We solved it in MATLAB. Keeping just the angular flux solution would require 4.4 terabytes of terabytes on your laptop. I don't have that on my laptop in general. So that's just the flux vector, right? Imagine actually trying to operate, form the matrices. And in a transport code, you actually never form these operators. You do the matrix vector action of them, but you don't have to do it here. You can actually form these matrices in this compressed form. So using a MATLAB implementation of the tensor train operators, we solved this on a 10-core i9 processor, 32 gigabytes of RAM. It's a pretty beefy laptop, but you're doing this in MATLAB as opposed to doing it in a compiled language like C++ and Fortran. So we see massive speeds up and reduction in memory. This is very promising. We're extending this to more general cases. Don't worry too much about the table. We're just showing that there's like the speed up factor. But the thing that I think is really interesting, if you want to actually store the matrix H, which in this case is the left-hand side of the transport equation, you'll end up with zettabytes. if you were to actually be, store this matrix in memory. I don't even know what zeta actually stands for at this point, but we're not constructing it. And then I said we would need 4.4 terabytes to store the angular flux. In this specific case, we only need megabytes. So by writing that as, products, tensor products, we can actually massively compress this. This actually might have a lot of applications where, instead of writing the entire angular flux to file, which sometimes people want for analysis, you would write the compressed form and then just reconstruct the full form. So even if computationally you don't care, there might be a lot of input, IO like benefits. To getting towards the end of my presentation, LANL right now is really big on postbacks, right? So, not for you, all your grad students, right? But if you were coming out of undergrad, not quite sure if you wanted to go to grad school and you wanted to go work and make some money, Los Alamos now has postback positions. Last year, I had a postbac, Leo Tunkel, who's now a PhD student at the University of Michigan, whose objective was to use machine learning to determine optimal group structures for problems of interest, using criticality benchmark problems. So, Los Alamos is usually a 30 group structure that has worked well enough for us, right? So imagine taking the energy domain from 0 to infinity and then picking 31 segments of it and saying, like, these are my group structures, right? You've introduced some sort of approximation that maybe you understand and maybe you don't, but it might not be the best for all problems, right? So why not use machine learning, in this case, hierarchical agglomeration and division, on a different sets of problems to figure out what is the best, if there is a best multi-group cross-section group structure. Spoiler alert, there isn't. It's problem dependent. I think we all sort of know that that's what machine learning gives you, but I think the process was very interesting. So what the student did, with our help, he trained on a criticality assembly called the BERT ball, which Los Alamos has, and he did this interesting thing where he took 618 groups, like the full multi-group library, and tested, random selections of 30 groups. So you can imagine how many, if you have 618 groups and then you pick 30, it's 618 choose 30. I think there's fewer atoms in the universe than that. So you can't do that, right? But he selected the 1,000 just to see whether or not by random chance you could select a group structure that performed better according to some error metric. So here, this is the distribution of different group structures. The black line is LANL 30, which is the thing that is traditionally used in the lab. Turns out that there's actually quite a bit of group structures that actually do far better. And this is by random selection, right? So instead of doing random selection, use machine learning to see if you can maybe find these group structures. And the details don't matter too much, but the idea is like train on a criticality benchmark assembly problem that you like, and then apply this to other criticality benchmark problems that theoretically are similar, and see how these like the trained group structure does. And it turns out it can do pretty well if you have the same neutron energy spectrum, and it doesn't do so well if you don't have the same neutron energy spectrum. I think the lesson here is that machine learning is very powerful, but at the end of the day, the reason why it didn't work is a physics reason, and you should well know why that physics reason is there. So we're not going to be replaced by AI just yet. I think we have 10 years. And so that's basically what we're saying. For machine learning, we can do pretty well for the set of problems that we studied, but we've introduced bias because we picked problems that we were interested about. We picked criticality benchmark problems because they're quote unquote well known. We've already introduced some sort of bias that the machine learning might pick up on. Random group structure generation can sometimes can do better, and the machine learning algorithm doesn't do better. Why is that? Well, it's because the algorithms in machine learning that we were using are called greedy. So at each step of the learning process, it was taking the optimal step to reduce the error, but it turned out that the actual minima wasn't you couldn't get to the minima that way. So you have to be careful what your machine learning your algorithm limitations. Also, the error function is actually very important. If you only care about K effective, you can nail that pretty well. But what if you actually care about leakage rates or reaction rates? The more you introduce into your error function, maybe the better representation of physics it is, right? But also, what are you forgetting about? Like, what is important that you don't know about? And that's like a very difficult question to how do you not know that you don't know something, right? But your machine learning algorithm doesn't care, so you should be able to interpret the results knowing that there is some information that you don't know. Once again, we're not going to be replaced just yet. And so all of this, right, just to generate a set of group structures that work well for some problems and not the others. I think the benefit was in the processes and understanding that the physics has a lot to say about what is an optimal solution strategy and how do you leverage that, right? That means building intuition in the problems that you're looking at. We're going to do similar work looking at weight functions. When you do the multi-group approximation, you collapse the cross sections using some weighting spectrum. The ideal one would be the solution to your, to the transport equation. You don't have that. You make some sort of approximation. Once you've introduced that approximation, you've introduced an error. Can you use machine learning on that weight function to maybe find some interesting physics? Maybe it can pick out, weight functions are functions of energy. If you have a thermal system, you expect to have higher weighting in the thermal spectrum. Maybe machine learning can tell you something about the physics of the problem that is not entirely obvious to you, from the start. And this is the future, future interest that we're looking at. So we're looking at things for like neutron scattering. One of the assumptions in transport is that the neutrons don't collide with each other. But in things like supernova, where you have a lot of neutrons, they actually will start colliding into each other. How do you solve that transport equation? It becomes nonlinear. What does it mean? Like, what is the cross section for that process? What does that mean? We're curious. We want to solve these sorts of problems. We want to do time-dependent multi-group weighting functions. As in the reactor, as it evolves over time, the spectra changes, right? Why are you using the group structure from time zero at time at the end? Can you instead have it change with time? We're relativistic moving material corrections. Like I said, when the neutron is in a fluid that is moving very fast, like in a supernova, it might be relativistic. That means your neutron is also going relativistic. How do you solve that transport equation? And we also have collaborations with NEN2, which is an experiments group, designing their experiments for non-proliferation. So we're working with them. We're also working with neutron diagnosed subcritical experiments, giving them insight and some like benchmarks on like the experiments that they want to design that they're actually building. And we also have a current project. If you come to Pfizer in April, a student of mine worked on anisotropic fission. One of the assumptions that you make is that the neutrons emitted in fission are isotropic. What if that's not the case? There's data, there's physics to show that that's not the case. Does it impact criticality? Does it matter? Should we care about it? But this is all in the goal of removing one more assumption from the transport equation and to get to a closer and closer approximation of the physics as it actually is. So this is me selling LANL, internship opportunities at Los Alamos. We have had many students from various nuclear engineering programs. We recently hosted students from the University of Mexico. That makes sense since it's close. Michigan, Imperial School, London, and Texas A&M. There's actually been no UIUC students, at least in my group, since I've been there, and I've been there since 2019. If anybody's interested, come talk to me. We always have a lot of summer internship opportunities. It doesn't have to be related to your dissertation. It could be related to your dissertation. We're always looking to get people out to the lab, to come out to spend 12 weeks at Los Alamos and to see what we're all about. And so these are some of the summer student research ideas that we've had. One of the things is we want to do 2D momentum advection on GPUs. So you not only learn about the moving material correction, but also how to solve that equation on a GPU. So it's HPC and physics. Stochastic neutronics, you're doing moments of neutron counts. How do you add dead time into these equations, right? To take into account that your detector does not immediately detect a neutron. We also have work on modeling 3D point sources in reduced geometry. This is like, if I have a source in 3D, can I solve an equivalent problem in 2D and preserve some of the mathematical properties of that solution? Maybe not. We're doing higher order alpha eigenvalues and k-effective eigenvalues. As we know, you can expand, the solution in eigenmodes, but getting just k-effective or alpha, the first alpha eigenvalue is very expensive. Can we use tensor train to go ahead and do, something like a QR iteration to get higher and higher eigenvalues and then expand, solutions in those. Multi-group data, application-dependent weight functions, sort of what we were talking about. Ultra-fine group data and collapsing on the fly. What if instead of doing multi-group, we start with the full spectrum and then collapse when we figure out what kind of problem we're dealing with? That might work. Generating new fission product data for Los Alamos. And anisotropic, we're still continuing the work in anisotropic fission. There's a lack of data, but we still want to evaluate the importance on various critical systems. And so if you want to come into the lab, there's actually various ways to get there. It's just not an internship with, through CCS. There's a bunch summer schools that are for grad students might be really interesting. It's a mix of lectures and project work. This is a relatively competitive selection process, but you end up in a cohort that's 20 to 30 students for 12 weeks, and you're paired with a mentor. That means that you spend half your time working with another person, usually not from your field, on a project usually not related at all to your dissertation or your research, but HPC and physics, computational physics related, with a mentor. You spend that 50% of the time doing that, but you also spend 50% of the time in lecture courses taught by different experts at the lab in things like plasma theory, neutron transport, Monte Carlo methods. So it's a really good academic experience. There's also just graduate internships where you come out with a mentor with a project in mind, less structure than the schools, no formal lectures, but you're still allowed to attend any lectures you want, but you come out here with an idea, we work on it for 12 weeks, you end up with a poster presentation or an oral presentation. That's just you finding a mentor that you work well with. Maybe not for this group, post-bachelors and post-masters, these are 1 to 2 year appointments. For undergrads, it's usually for those who are not sure if they want to go to grad school. You come out and they get to sort of do, kind of graduate research, and then you get to decide whether or not this is for you. And so far, we've had 100% success in sending people to grad school after they do the 1 to 2 year appointment. We also have postmasters. We haven't had a postmaster student yet, but there's these opportunities available out there, especially if you're finishing up in a bachelor's degree program and you're not quite sure you want to do the PhD. This gives you 1 to 2 years to, either get your resume, if you want to get, your resume to look better, or you want to learn a skill, this is the time to do it before you apply to graduate schools or before you want to apply to a job somewhere. They're all temporary positions, I will note. These, after 2 years, you might be hired in another position in the lab, but you cannot say postbac or postmasters forever. Postdoctoral, this might be really important for you all. We have tons of postdoc positions. It's generally 2 to 3 years to work on research with a designated mentor. Sometimes it has to do with your dissertation research if we're also interested in it. Sometimes it doesn't, right? You could go out there and do something completely different, orthogonal to what you're doing, but you have 2 to 3 years to focus on that one specific problem, to publish as much as you can, to learn about the lab, and then you can decide whether or not you want to be part of the, the lab for your long-term career. And so we're always looking for good postdoc candidates from varied fields, nuclear engineers, of course, but also applied mathematicians, physicists, anybody who can probably, hack it with computational physics. We're willing to talk. And with that, that's it. Any questions? Thank you for listening to me.